In this problem, we're considering a ladder that's leaning on a wall. There's a 70 kilogram painter who's using this 13 kilogram ladder to paint the outside wall. The ladder is 7 meters long. It's not 7 meters off the ground, but it's 7 meters along the slant of the ladder. The coefficient of static friction at the wall on the top of the ladder is 0. It's a slick wall. The coefficient for static friction for the ground and the bottom of the ladder is 0.3. The painter is standing on a rung on the ladder 4.8 meters along the slant, up from the bottom of the ladder. And this, again, is not 4.8 meters vertically, but it's along the slant of the ladder. Your task is to calculate the minimum angle that the ladder can have with the horizontal ground and not slip. We know we could stand the ladder pretty much vertically and it wouldn't slip on the ground, but we're interested in how far away the situation will be. The base of the ladder is farther away from the wall. What is the angle that we can have, the minimum angle that we can have, such that the ladder does not slip and the painter crashes to the ground? So we'll set this up with a picture, of course. It's always advisable to draw a picture and label it. It doesn't have to be a great picture, but we have our diagonal or slanted blue line here. That's the ladder. And we identify the forces that are present here. At the bottom of the ladder, the ground is pushing up on the ladder. That's a normal force. There's static friction at the base of the ladder. So friction, static friction, H horizontal is my notation here. And that frictional force is going to be acting to the right. Static friction acts in a direction to minimize motion, and we want the ladder to stay there, so we need a force off to the right to hold the ladder in place. We have the mass of the ladder times G gives a weight acting down at the center of mass of the ladder, and we have the painter, mg for the painter, the weight of the painter acting vertically downward. At the top of the ladder, in the general case, the wall is pushing to the left on the top of the ladder. In the general case, there will be static friction vertically upward acting at the top of the ladder. Testing your memory here, what do you know about the static friction vertically at the wall here? Well, in the wording of the problem, it said that the coefficient of static friction of the wall is 0. So in the future diagrams, you won't see this force and arrow present in the diagrams. It simplifies the problem, and we're going to work it that way. We have SV equals 0, and I'll eliminate that in future slides. So we have three unknowns here, technically. We have the force of the wall going to the left. We have the force of static friction horizontally at the bottom going to the right. And we have the normal force going up. Which of these would be relatively easy to calculate given our data? Well, you should say F sub n is in the vertical direction. Let's go to the next slide. We just have those three forces. The ladder is not supposed to be moving, so its acceleration is 0. So the sum of the forces equals 0. In the vertical direction, I'm going to choose upward as a positive direction, the normal force, and then we have the weight of the ladder acting down, so I give it a negative sign, and the weight of the painter acting down, I give it a negative sign. And we know some numbers here. We know the mass of the ladder, we know the acceleration due to gravity, we know the mass of the painter, and again the acceleration. So you might want to pause and put this into your calculator. I came up with 813.4, and I should have put newtons here. Sorry about that. Newtons were in the metric system. In the horizontal direction, there are only two forces. So I'm going to choose to the right to be the positive direction. So we have static friction horizontal minus the force of the wall as a negative because it's acting to the left, and there are two unknowns there. Well, I need some more equations. What about the rotation of the ladder? It's supposed to be stationary, so it will not be rotating. So the angular acceleration, this is an alpha, the angular acceleration will be 0. For angular acceleration to be 0, the sum of the torques must equal 0. And torque, choosing the axis at the ground. So we're going to put an imaginary point here at the bottom of the ladder. That's where I'm going to put my axis. And I'm going to let the clockwise torques be positive. Anything that would tend to move, to rotate the ladder in a clockwise direction given this pivot point, I'm going to call positive. What about Fn and Fsfh? What about these forces? Do they have torques? Do they create torques? No, because torque is force times lever arm, and these forces act at the axis. Their lever arm is 0 meters. So here we go with the torques. We have the weight of the ladder. What is the effective lever arm for this weight? Well, I'm looking for a perpendicular distance back to the pivot point, and that's right here at the base of this small triangle. The base of the small triangle is the lever arm for the weight of the ladder. To find the lever arm, you just imagine in your mind, draw this force arrow down and find the place where there's a perpendicular line back to the pivot point. What's the length of this? Well, the ladder is 7 meters long, so the center of mass is 3.5 meters up along the ladder. Here's our theta. Cosine of theta multiplied by this hypotenuse of 3.5 meters produces this lever arm, the distance here at the bottom of this small triangle. In a similar way, the painter has a lever arm, but now the painter is 4.8 meters up from the base of the ladder. So 4.8 meters is the hypotenuse times cosine of theta. That gives us the lever arm for the weight of the painter. And then we do have to consider this FSV in general. It's sitting at the top of the ladder here. And the vertical force, remember, I've told you I'd erase it, and perhaps I did it too soon in this diagram, but it's 0. It does have, in your mind, a lever arm, and it would be 7 meters and cosine of theta. Here's its lever arm all the way across this base of this big triangle. But it's 0, so this term's going to drop out. The force of the wall survives. So the force of the wall here is going to have a torque. And again, doing its line of action, the straight line horizontal across here, its vertical distance is this distance in the diagram. It's this side of the triangle. To get this side of the triangle, we multiply the length of the hypotenuse times the sine of theta. So a little different trig function to find the lever arm for F sub W. Okay, let's go a little further. The Fn and F sub h again have 0 torque. I've gone ahead and I've put in the numbers, so I'm going back here. You might want to do this on your calculator. Put in the mass of the ladder, 9.8, the 3.5, multiply those together. The mass of the painter, 9.8, and the hypotenuse for the painter, and multiply those out. And we come up with this next expression, this equation. 445.9 times cosine of theta plus 3292.8 times cosine theta minus 7 FW and sine of theta equals 0. In working these problems, I tend to keep 4 significant figures at least, and really when I work it on the calculator, I don't bother rounding. I just continue the calculation. I'll round off the final answer to 3 significant figures. But in intermediate calculations, I don't do that level of rounding. I don't want to create round-off error. So let's go a little further. Well, F sub n, we found that on the early slide. It's equal to the sum of the weights of the ladder and the painter. And here's just recopying this same equation from the previous page. And then looking at this minimum angle, we're going to use as much static friction as possible. So usually you see static friction expressions with the force of static friction is less than or equal to the coefficient of friction times the contact force, the normal force. Well, at the minimum angle, we need a lot of static friction. We need the maximum amount of static friction. So the force of static friction horizontal will be the coefficient of friction times the normal force, 0.3 times the normal force. Let's go a little further. Just recopying some of the previous results. And here I'm just switching things a little bit. This force static friction horizontal, numerically, that's the same as the force of the wall. They have opposite directions, but as a number, they're the same amount. So I'm making a substitution. And we come up with force of the wall then equals 0.3 times the normal force, which we found in an earlier slide, 813.4 newtons. So the force of the wall, 244 newtons. And we can continue our calculation here. This is just recopying an earlier equation. But now we know F sub W. So we're going to go ahead and substitute that in. You might want to pause and on your own substitute in F sub W and see what expression, what equation you come up with. So you should come up with, in putting these numbers together, the cosine theta terms have coefficients that can be added together because we have the same variable here, cosine theta in both terms. So 3738.7 times cosine theta. And now moving this negative term over to the right and doing the multiplication, 7 times 244, we get 1708 times sine of theta. Well, can I change this around a little bit? What if I would divide both sides by sine of theta? What if I divide both sides by sine of theta? And also if I divide both sides by 1708. If I divide both sides by 1708, I come up with 2.189. Oh, I'm sorry, I made a mistake. Divide both sides by cosine theta. Divide both sides by cosine theta. So I get just a 1 over here. The cosine theta divided by cosine theta is a 1. Sine theta over cosine theta, that's tangent. So I left out that step on the slide. I'm putting it in verbally. Divide both sides by 1708. Divide both sides by cosine theta. And then we would have 2.189 equals tangent theta. 2.189 equals tangent theta. You might want to pause and write that down on a piece of paper. I'm trying to find theta. I can't get an answer if it's embedded in this tangent function. 2.189 equals tangent theta. How do I get theta out of the control of the tangent function? I apply inverse tangent to both sides of this equation. It's important to do it to both sides. So inverse tangent of 2.189 equals inverse tangent of theta. This right side reduces just to the theta, the answer I'm trying to find. And if you put in your calculator into degree mode and do inverse tangent of 2.189, you find 65.4 degrees. There's our angle. That is the smallest angle we can have for this ladder. If we would pull the base in such that the angle is maybe 75 degrees or 80 degrees, we wouldn't need as much friction. But if we're using the maximum amount of friction, as we must do when this angle is a minimum, we find that minimum angle is 65.4 degrees. I hope that you've followed along. You might need to back up the video and replay some sections, but that's our answer, 65.4 degrees. So I've got many more lectures, short lectures, and example problems worked out for physics and astronomy. And I've got some recreational amateur astronomy videos also, and a lot of videos. There's an annotated list of my YouTube videos at my simple website, gpclements.com. You can use a desktop browser or you can use your phone. It's a responsive website. And the annotated list has a link, a direct link to the YouTube videos. So you can just click on that link and the YouTube video will start playing. You don't have to search for my videos on YouTube. The annotation tells you how many minutes the video is and gives a little description of the content of the video. All this content is free. You're not allowed to resell it, but you don't give me your name, you don't give me your email address, anything. You don't pay for these, and my website does not put cookies onto your computer. So I hope you keep working physics problems. Ask your instructor if you have questions.